Hello and welcome to ICND2 Lab 7. This lab explains the NAT Overload feature, which is also called Port Address Translation, or PAT. Note that the details discussed in this video are also explained in the Cisco Press ICND2 Exam Certification Guide, Chapter 16.
Like most labs, this lab has several objectives. First, NAT uses a lot of terminology that can be confusing, so we'll start out with some definitions of the terms inside, outside, inside local, and inside global. Then the lab will talk about how NAT changes things in the IP packet, in particular IP addresses as the packet passes from an enterprise host to an internet-based host, and vice versa, and how the router, when performing overload, will change port numbers so that it can support multiple TCP connections over a single routable IP address. Then we'll take a look at the NAT overload or PAT configuration, in particular the style of configuration that uses a router's single interface IP address when translating IP addresses.
The scenario for Lab 7 has two basic steps.
For the first step, we'll begin with a working internetwork that already has NAT configured. Using this internetwork, I'll describe the terminology used with NAT, as well as the concept of how NAT changes both IP addresses and port numbers. After that, we'll circle back with the second step and look at the configuration used in that sample internetwork. This lab uses a relatively simple topology, but the complicated part comes in when you think about how NAT translates addresses and port numbers. First, on the left, we have a typical enterprise network that's using a private network number, in this case network 172.22.0.0. None of the addresses in this range will be reachable by the rest of the internet, so NAT will have to change those IP addresses. Next, you see a couple of routers. R1, the enterprise router, connected via a point-to-point link to some ISP. The IP addresses you see there in that link are publicly routable. So in the internet, as you see here on the far right, those hosts will be able to send packets to the IP addresses in network 100 that you see in the figure. In particular, they'll be able to send packets to 100.112, R1 serial IP address, which will be used as the inside global IP address with NAT. To understand NAT terminology, you need to think like an enterprise network engineer rather than the ISP's network engineer. If I'm the enterprise engineer, I think of my network as the inside network, inside being a key term within the NAT world. Then I think of the rest of the world, the rest of the internet, as the outside network. So there's inside my network and outside of it, which is the rest of the world. Now, if I think about a host that sits inside my network, when it sends a packet, that packet's got a source and destination IP address. And that source address in particular is going to need to change to an IP address that's globally routable. So I'll use two different terms to describe that. First of all, on the inside, I'm going to use the term inside local to describe that private IP address, in this case in network 172.22. But as the packet passes through router 1 is going to change that source address. It's going to change it to a different address called the inside global address. That address represents the inside host as it goes through the globally routable internet. Now in this particular example, we're going to change that IP address to 100.112, which is router 1's serial IP address. Next, in order to get a much better understanding of how NAT overload works, we'll take a look at two different TCP connections. The first connection goes from PC1 on the left to the web server on the right. The lower left-hand side of your screen shows the packet that's sent from PC1 to the web server. Notice the destination IP address is the server's IP address, and the source address is the inside local address of 172.22.11.101, or in other words, PC1's IP address. Now PC1 sends this packet with a TCP header, destination port 80, which is the well-known port for web services, and PC1 also allocates a dynamic port number of 3212, coincidentally in this case. Now when this packet arrives at router 1 decides it wants to do NAT for this particular packet. So router 1 starts to build a NAT table entry based on that packet, copying the source address and source port number of the packet into the inside local column of the table. Then router 1 changes the source IP address to the inside global IP address of 100.1.1.2. Now in this case, the port number does not need to change, so the inside global entry has the IP address 100.1.1.2 with the same old source port number. So this table entry represents how router 1 will change the packet as it goes left to right through this particular picture. The second TCP connection shows the need for translating the port, hence the name port address translation. PC2 now connects to that same web server. PC2's packet, as you see on the lower left there, has the same destination address, but PC2's source IP address. That, of course, will be the inside local IP address. Also, the destination port's 80, and coincidentally in this case, PC2 happens to pick the same source port number as did the first connection, and that'll be important to the process. So we see the router 1 starts to build its NAT table entry for the second connection, as you see there on the left-hand side of that table. As router 1 performs the NAT function, it changes the source IP address to the inside global IP address of 100.1.1.2. However, router 1 notices that there's already a different TCP connection that's using port 3212 with that inside global address. So router 1 knows it needs to use a unique port number for each connection, so it also changes the source port number for the second connection, in this case just to 3213, just to have a different number. So as you see there, router 1, when it's performing NAT, changes both the source IP address and source port number, hence the name port address translation. Also note that these two TCP connections both are using the same inside global IP address. In fact, you can have around 65,000 concurrent TCP connections sharing that same IP address, which is how NAT Overload, in other words PAT, saves on globally routable IP addresses. Next, take a look at an example from the command line interface. To begin, if we go to the NATing router and do a show IPNAT statistics command, you'll notice that there are no active translations, which means there are no entries in the NAT table. If you look further down, you see a hits and misses statistics counter of 0. Misses occur each time a new TCP connection occurs because there's no entry in the NAT table. Hits occur when a packet shows up and there's a matching NAT table entry. Now, as I mentioned before, there are no translations right now, so the show IPNAT translations command simply lists no output. Next, not shown on your screen, I'm going to walk over to PC1 and PC2 that are shown in the figure and create a couple of TCP connections. In particular, I'm going to go to PC1 and create one TCP connection that happens to use source port 15,916, a second TCP connection from that same PC1 with a different port number, in this case 35,203, and then a third TCP connection, this one from a different PC, PC2, with a source port number of 13,109. Now that I've created these, we should be able to go back and look at router R1 and see 3 NAT table translation entries. Now that the connections are up, let's take a look at the output of the show commands on router 1. The show IPNAT translations command now lists 3 translations. If you look at the left-hand column where the inside global IP addresses are listed, notice all 3 translations list the one inside global address, namely 100.1.1.2. If you look at the inside local column, you'll see 2 entries that list the .101 address, which is PC1, and a single entry that lists the .102 address, which is PC2. If you go back over to the global column, you'll notice that 3 different port numbers are used for each of the translations. And in fact, if you look at those port numbers and compare it to the inside local column, it's the same 3 port numbers. In this case, none of the port numbers bumped into each other, so NAT did not have to translate any of the port numbers in order to make the NAT-PAT function work. Next, let's take a look at the output of the show IPNAT statistics command. Notice there are values there for the hits and misses now. The miss counter increments every time a new connection shows up, and the NATing router must create a new NAT table entry. The hits counter increments every time a packet shows up, and the router already has a NAT table entry. Now, we don't see a lot of hits. It turns out I brought up the TCP connections and brought them right back down. So if you look toward the top of the output, you'll notice the entry that says total active translations of 0. That means during the time it's taken for me to record this particular session that all the NAT table entries have timed out. If you look down a little bit further in the output, you'll notice the expired translations area. It says that the 3 connections or 3 NAT table entries I had before have expired. If I go back and do a show IPNAT translations command at this point, you'll note that there are no longer any entries in the NAT table. Next, let's take a look at the configuration used on R1 to perform the NAT functions you just saw. First of all, you have to tell router 1 which of its interfaces are in the inside part of the network and which are outside, and that tends to be relatively simple. All you need to do on router 1 on its inside interfaces is add the IPNAT inside interface subcommand, and on the outside interfaces, like the serial interface on the right, use the IPNAT outside command. At that point, you have to go use the most complicated part of NAT, which is the IPNAT global configuration command. Now, to configure NAT as we've seen in this example, you'd use the inside and source keywords. The inside keyword says to NAT or translate the packets entering inside interfaces, and in particular as they enter inside interfaces to change their source IP addresses. So the hosts on the left of the diagram we've been using as they enter the router's LAN interface will have their source addresses changed, just like we've seen. Now the NAT function can be restricted to a subset of hosts that are inside hosts. So the list ACL number parameter says these are the specific hosts. Now in most implementations, typically this access list will match all inside hosts, but it doesn't have to. In our case, we will have an access list that matches all of the IP addresses in Class B network 172.22. In other words, all the inside hosts. Next, the IPNAT command defines the inside global IP address or addresses. In this case, since we're using a single inside global IP address, we're going to simply use the interface parameter. The interface parameter will point to R1's serial interface, and from that interface, the router will say, oh, I'll use the interface IP address as the inside global address. Finally, once you type the overload parameter at the end, it says let's also do the NAT overload function. In other words, let's do port address translation as well as need be. So let's take a look at the output of the show run command. If you page down just a tad, you'll see the interface output. So first let's focus at interface fast Ethernet 00, which is the left-hand LAN interface on router 1 in the diagram. Notice the IPNAT inside command places that interface as an inside interface and makes it be part of the inside part of the network. If you look a little further down on serial 010, which is in the outside, you'll notice the IPNAT outside command. Now that's the easy part. If you scroll further down, you'll see the IPNAT inside command. Notice the inside and source keywords of that command tells the router the following. For packets coming in the inside interface, change the source IP address. So we've seen examples of that throughout this particular lab. Then if you look at the list 3 parameter, it tells the router, alright, only perform that NAT function for packets whose source address matches access list number 3. Now if you're using the Cisco Press Exam certification guides, you won't have gotten to the chapter that covers ACLs yet, but it can be relatively easy to understand in this example. If you look just a few lines down, you see access list number 3. And this access list essentially says match any packets whose IP address begins with 172.22 regardless of what's in the 3rd and 4th octets. Now in this case that means all packets from the inside part of the network that's shown in the left hand side of the pictures. So essentially all inside hosts will be NATed. Now if you look a little further in the IPNAT command, you'll notice the interface command that lists interface serial 010. Now that's a reference to say the inside global IP address will be serial 010's IP address. If you look up a few lines, you'll notice interface serial 010 again, and you'll note there it lists the IP address that will be used for the inside global address. Finally, if you stop there, you've configured NAT, but if you include the overload keyword shown on the end of the command, you also configure NAT overload or PAT. The overload keyword tells the router, alright, also translate the port numbers so that you can multiplex around 65,000 concurrent connections using a single globally routable inside global IP address. In this lab, we've defined several NAT terms including inside, outside, as well as inside local and inside global IP addresses. We've also shown you how NAT changes both IP addresses as packets flow from the inside to the outside parts of the network, as well as port numbers as need be in order to multiplex lots of different connections over a single globally routable IP address. We've also looked at the configuration for NAT overload, in particular the configuration that uses a single interface IP address as the inside global address.